This video will cover Chapter 13, Inference for Relationships Between Two Quantitative Variables. We'll talk about regression for the sample versus for the population. We'll talk about modeling for populations and how to use, how to estimate parameters. We will look at the null and alternate hypotheses for doing hypothesis tests for regression. We'll talk about how to test about the slope and interpret the output. And we will compute confidence intervals for the slope. After that, we'll talk about prediction intervals for individual responses and confidence intervals for mean responses. We'll talk about what will cause the explanatory, what will happen when the explanatory variable is close to or far from the mean, how that affects the response value. We'll talk about how to approximate the intervals, that is the prediction intervals and the confidence intervals, by hand. We'll talk about the relative widths of the prediction intervals and confidence intervals. And we'll look at a list of guidelines for when we can perform inference for regression. In the 4 stages of statistics, we are now looking at statistical inference, relationships between two quantitative variables. Recall that when we're looking at a relationship between two quantitative variables, we'll display the relationship with a scatter plot. And we summarize the relationship with either, in words, we'll talk about whether the shape is linear or if it's curved. We'll talk about the direction being positive or negative. Remember, positive means the slope is positive. In other words, as we go from left to right, the response values go up, so this is positive, and a negative relationship as we move from left to right, the values go down. Remember, we talk about the strength of a relationship, whether it's strong, moderate, or weak. The correlation R gives us both the direction and the strength. Also, we can compute the least squares regression line, the linear regression line, which allows us to predict a y value for any explanatory value x. Once we have the equation of the regression line, which we will write this way, y hat equals b sub 0 or b naught plus b1 times x. This line is chosen so that the prediction errors, those are the residuals, so that's the actual y value minus the predicted y value. When you take those errors and square them and then add those up for all the points, the least squares regression line is the one that minimizes that total. We can find the typical residual size, it's called S, and it's computed this way. That looks a lot like the formula for the standard deviation, and it is, the difference being this 2 in the denominator. Notice there are no x's in here at all, just y's. The slope, that b1, we can interpret as the change in y for every change in x of 1 unit. The intercept is what we would predict when x is equal to 0. Sometimes that'll make sense and sometimes it won't in context. Remember that this line, the least squares regression line, is the line that best fits the points in our sample. That doesn't mean it's necessarily the best line for the population. Because we only have values for the sample, we can only find a line that fits our sample. If we want to make a guess as to what the unknown population looks like, we're talking about statistical inference. So here's an example of a sample. We have parents' ages. On the horizontal axis, we have fathers' ages, and on the vertical axis, we have mothers' ages. For this particular sample, the red line is the actual slope of the least squares line for the sample. We don't know what the population looks like. It could be a little higher. A higher slope would be the dotted line that is on top here. on the right side. It's also the one that's on the bottom on the left side. Or the slope could be a little bit lower. We just don't know. So to answer the question, is this the slope that best fits the relationship for all students' parents' ages? Well, no. It might be bigger, it might be smaller, but it's going to wiggle. So, what about for the intercept? We have a guess for the slope, but if you change the intercept of a line, all it does is slide the line up or down. It doesn't change the angle. So is 14.54 the intercept of the line that best fits the relationship for all students' parents' ages, that is for the population? Well, we don't know. For the sample, it's 14.54, so we can assume that for the population, it should be close to that. It might be a little higher, in which case the line would move up. It might be a little bit lower, in which case that line would move down. So there's a higher one. There's a lower one, could be somewhere in between. So remember that S is the typical residual size. That tells us how far away the points in our sample are from the regression line in general. So is 3.3 the typical prediction error size for the population? Well, again, we don't know. It might be a little bit smaller. It might be a little bit bigger. But we can guess that it's probably close to 3.3. So when we're talking about the population, sigma is what we're going to call the typical residual size in the population. It corresponds to S in the sample. And instead of using y hat and b naught and b1, we will denote the equation of the regression line in the population as mu sub y equals, that's a Greek letter beta right there, beta naught plus beta 1x. So if we know what x is, we can plug it in, and that will give us a mu sub y. That would be the mean y value of all the responses with that given x value. The standard deviation of those responses with that corresponding x value would be sigma. This table shows you how to draw the comparison between symbols we use for parameters, that is for the population, and symbols for the estimates, that is in our sample. So the thing to remember is that for any given x value, so let's say an x value of 55, that'll be right about here, we can go up to our line and we get a distribution of possible y values. Overall, you can see that those y values are higher than the corresponding y values for a father's age of, let's say, 40. They're clustered around the line, and they should be normally distributed. So for the normal distribution for this given x value, the mean of the distribution is the predicted value, what we get when we plug our x value into the formula for the line. And the standard deviation of the distribution is sigma, which we will approximate using S. So for the intercept and for the spread, that is for B naught and sigma, we can use point estimates, and they're usually good enough. So whatever we get for B naught, that's a good estimate for beta naught. Whatever we get for S, that's a good estimate for sigma. For slope, though, this is where we're going to want to do hypothesis tests or confidence intervals to see if there actually is a linear relationship in our data. When we want to perform a hypothesis test for a relationship between quantitative variables, the null hypothesis is always the same. That beta 1, that's the slope of the regression line in the population, is 0. If the slope of the line is 0, that means that the term on the end there that has the x in it disappears. You multiply by 0 and it goes away. That means that the mean y value only depends on beta naught. It doesn't depend on x at all. That means that there is no relationship between x and y. Remember, we learned once upon a time that the slope of the regression line, that's B1, is equal to the standard deviation of the y's divided by the standard deviation of the x's times r. So if the slope of that regression line is 0, the only way that can happen is if r is also equal to 0. So sometimes you will see that null hypothesis framed that way, that r equals 0. The alternate hypothesis might be one of three things. That the population slope is greater than 0, less than 0, or just different from 0. Another way to say that is that x and y are related in the population. If we choose one of the first two alternate hypotheses, we might also be able to say that the relationship is positive or negative. Here's an example. Here's the computer output for the mother's age versus father's age that we've seen before. What are the parameters that we're interested in, and what are the estimates for them? And what hypotheses are we going to test? Well, there are three parameters that we're interested in: the slope, the intercept, and the standard deviation. For the intercept, remember, we can use a point estimate. The intercept we will estimate to be the intercept for our sample, which was 14.542. For the slope, we can estimate that it is the same as the slope in the sample, 0.66576. The standard deviation we can estimate as S, the typical residual size. That's 3.288. So the hypothesis test we would do is, as always, the null hypothesis would be that the slope in the population is 0. And maybe we have reason to suspect ahead of time that the slope is positive, so that would be our alternate. Remember that for doing hypothesis tests for one quantitative variable, the p-value that we sought is the probability that we would see a sample mean as weird or weirder than the one that we observed in our sample. In order to find that probability, we had to know how the sample means were distributed. In other words, what is the sampling distribution of the sample means? Now, to do inference for our slope, we also need to know something about the sampling distribution. How are the slopes distributed? Well, the slopes will vary. Remember that for each given x value, we will assume that the y values are distributed normally. But the slopes might vary some. It might be steeper than what it looks like in the sample. It might be less steep. So how can we estimate that distribution? Well, you can take it for granted that the sample slopes have mean equal to whatever the population mean is, and standard deviation, which approximately equal to the standard error for B1. That's the standard error for the sample slope, which is computed in this way. It's S, that's the typical residual size, divided by the square root of the sum of the squares of the deviations of the x's from their mean. Whew, that's awful. Don't worry, you won't have to compute that by hand. In the numerator, notice there's S. That is our typical residual size. That means if the residuals are large, that makes that fraction bigger. That increases the standard error for the slope. That means we'll have a more possible variation. If the residuals are small, that is, if S is small, then there won't be as much wiggle room for that slope. We can also assume that the slopes are approximately normal if two things. Either the responses vary normally around the line, that is, for each x value in the sample, the corresponding y values are distributed normally, or if n is large enough. So this is what it'll look like. Normal distribution centered at the population slope with standard deviation approximately equal to the standard error for our sample slope. So when we take a sample, we will get a slope in our sample, that's B1. We'll want to standardize that. We'll use t typically to standardize it, and we do it the same way we always do. It is the observed value minus the expected value over the standard error. And again, that's the standard error for the slope. Assuming the null hypothesis is true, the null hypothesis, remember, is that the population slope is 0, so that simplifies our computation a bit. When we're doing inference for linear regressions, we are going to use a t-test, but it's important to know that now we're going to have n minus 2 degrees of freedom instead of n minus 1 as before. So remember, if the slope is close to 0, that's going to give you a numerator in that fraction up there to be small, which means the p-value will not be small. So t is not big, that means the p-value is not small. It's actually big. If the slope is far away from 0 relative to the standard error, that's going to give us a big t-value, which will lead to a small p-value. So the big question boils down to, is the slope in our sample far away from 0? And we want to measure that far away from in terms of the standard error. Here is what the sample slopes will look like when they're distributed if we take a whole bunch of different samples. Once it is standardized, that means now we're looking at t. It looks like the t distribution, which looks like a normal distribution. Smaller peak, fatter tail, centered at 0 with a standard deviation or standard error of 1. So here again is that computer output. How do we read this? Well, up at the top, we see the equation of the line. Notice the slope is positive. Is it far away from 0? Notice that we do have a strong relationship. We get an R value of 0.78. Remember, 0.7 is our cutoff. We get a typical residual size of 3.288. So that'll be our prediction error. So now what can we say about the population? Here's our hypothesis, null hypothesis and alternate hypothesis. So remember, this is all about slopes. So we're going to look at the coefficient for father's age. That's the slope. So we're looking in there in the line for father's age. Our estimate for the slope is the coefficient. The standard error for the slope is given there under SE coefficient. It's 0.0257. Standardized, that's t, and look, we got a column for t. The standardized value is 25.9. Oh my heavens, that is huge. P-value to 3 decimal places is 0. That is just an enormous t-value. So, will we reject the null hypothesis? Oh yes, we will. That is a tiny, tiny, tiny p-value. So, can we conclude that there is a relationship between the variables? Absolutely. Now, we're going to be talking about strength in two different ways. The strength of the relationship between the two variables and the strength of the evidence that we have for such a relationship. Either one can be weak or strong at the same time. Remember that R tells us the strength of the relationship. We get that out of the sample. If R is close to +1 or -1, we have a strong relationship. If it's close to 0, it's weak. The p-value tells us the strength of the evidence that the variables are related in the population. Small p-value means strong evidence. In the example we just saw, we had an R value of +0.78 and a p-value essentially 0. This tells us, since R is bigger than 0.7, we have a pretty strong relationship. And because the p-value is tiny, we have very strong evidence that there is a relationship in the population. Notice that if we have a small sample, here we have just 4 points. This is percentage of people voting Democrat versus percentage voting Republican for 4 states in the 2000 presidential election. You'd expect this to have a pretty strong relationship, because if more people voted Democrat, fewer must have voted Republican, and vice versa. And sure enough, we see an R value that's really big, -0.922. So there we see the negative relationship, and it's strong. The p-value, though, is only 0.078. So what we have is evidence of a strong relationship, because R is close to -1, but the evidence that we have is weak. That's because we have a small sample size, a p-value not less than 0.05. Here we have a large sample. Here's heights of mothers versus heights of fathers. Again, we have a p-value of 0, but an R value of only 0.225. And looking at the cloud of points here, it doesn't look very strong. It does look positive, but it doesn't look strong. So here, in fact, we do have strong evidence, because p is less than 0.05, of a weak relationship because R is close to 0. So remember, the sample slope, B1, has mean beta1. That's the slope in the population. The standard deviation is approximately the standard error for B1, which we compute this way. The shape is approximately normal if the responses vary normally around the line, or if n is large. To construct confidence intervals for that slope, we'll use B1 as our point estimate, the standard error for B1 as the estimated standard deviation, and we'll choose the appropriate t multiplier with n-2 degrees of freedom. If n is really big, for a 95% confidence interval, for example, as always, we'll use 2 as our multiplier. So let's look at some of these confidence intervals. Remember, the confidence interval will be the point estimate, that's B1, that's our slope in our sample, plus or minus the right multiplier times the standard error for B1. The multiplier is coming out of the t distribution with n-2 degrees of freedom. If the sample size is at least 31 or 32, something like that, you can just use the z multipliers. So for an n, a big sample size, bigger than 31 or 32 or so, we can use a multiplier of 2. Let's look at an example. Here is the output for the parents' ages again. Let's give a 95% confidence interval for the slope of the line relating mother's age and father's age for all students, that is, in the population. Well, our sample size is 431. That's huge. So we'll just use 2 for the multiplier. We'll have the point estimate. That's 0.666 plus or minus the multiplier of 2 times, where did this number come from? That's the standard error for B1. And that gives us a confidence interval of about 0.62 to 0.72. So how do we interpret this? That means that we are 95% confident that the slope of the line in the population is between 0.62 and 0.72. That means if we increase x, in this case x is the father's age, if we increase the father's age by 1 year, we would expect the mother's age to go up by between 0.62 and 0.72. Notice that 0 is not anywhere close to this confidence interval. So there's a good chance we're going to reject the null hypothesis. And again, we saw that. The p-value right here is 0. There are two interval estimates that we're going to talk about for regression. So the situation is, I'll just write it in here for you. Given an x, what's the corresponding y value? This is kind of a tricky question. We can think of it in two ways. The first way is a prediction interval. If I give you the x, what is your prediction for y? I think it will be between what and what. So that's for an individual response. We might also say, of all the people in the population, or all the individuals in the population that share this particular x value, what do we think the overall average of that subpopulation, of just those people with that given x value, what's going to be the mean y value? For that, we're going to talk about confidence intervals. So that's the difference between a prediction interval and a confidence interval. These are computed in almost the same way. This is going to look very familiar. For a large n, bigger than, again, than 31 or 32, the 95% prediction interval will be y hat. Remember, that's what the line predicts for that given x value, plus or minus 2 times s. Remember, that's the typical residual size right there. For the mean, instead of multiplying the 2 by s, we multiply 2 by s divided by the square root of n. Look familiar? Remember, we're talking about means, and dividing by the square root of n, remember that was how we computed the standard error for sample means. So we have the same thing going on here. Notice that both intervals are centered at the predicted y value, at y hat. So we start at y hat and add and subtract the same number. Now keep in mind that our approximations may not be good if we have a small sample size or if we have an extreme x value. So here's another example. Here we have a property owner who has had his property assessed, and he thinks that the assessed value of $40,000 is too high. So to check if it's too high, he took a random sample of 29 lots in the area. The means of the areas of the lots were 5,619 square feet, and the average value was $34,624. So there you see those points plotted, and we have the regression equation. We have a very big R value, 0.927, and the typical residual size is about $6,700. So where is our property owner's property on this plot? Well, the size of the lot is 4,000 square feet. So we see that back down here. The assessed value of $40,000 is here. So we go across, we go up, and there is our property owner's property. Notice that's a pretty big residual. It's pretty far away from the line. So I think he might be right. Now, so notice that the 4,000, the size of the property, is below average, but the value of $40,000 is above average. That's pretty unusual because we had a positive R value and a big positive R value. That means we're not going to see many points on the plot with those properties. Below average X, but above average Y. So let's actually do some hypothesis testing. First, we'll do an interval. Property owner, again, has a 4,000 square foot lot that is assessed at $40,000. So we're given the regression equation for our sample of size 29. We got a really positive R value and a typical residual size of $6,682. So what range of values are within two standard errors of the predicted value for 4,000 square feet? Is 40,000 too high? Well, our Y hat, we plug in 4,000 and we get $25,000 roughly, a little bit bigger than that. The standard error for this typical residual size is S. So we're going to add and subtract roughly 2 of those. Again, this is approximate. The sample size is close to our cutoff for using 2. But if you go up and down by 2 of those standard errors, we get a prediction interval of 11,727 to 38,455. Notice that 40,000 is not in there. So I'm a little worried. I think our property value has been assessed too high. So here's our scatter plot again with the line. The red star is our property owner's property. If we wanted to, we could go on the scatter plot and actually plot the prediction and the range of values that we just talked about. The prediction is the point directly on the line above 4,000. And then we go up and down by 2 standard errors. We get a spread something like this. And there again, we see our property owner's value well above that range. So remember, the prediction interval will correspond to our 68, 95, 99.7 rule for individuals. It's where an individual response could be found. The confidence interval, though, is about the mean. If you take all of the individuals in the population that share that X value, what are their Y values going to look like? In general, the prediction intervals are wider because, remember, those are for individuals. There will be much more variation. But once you move to a mean, all of those, all the variation in the individuals gets canceled out. The high ones and the low ones cancel out, and they're going to give us a narrower confidence interval for that mean. So remember, both use information about X. We have a given X value to tell us confidence levels about the corresponding Y value. So the corresponding Y value, if we're talking about a prediction interval, or the mean of all the Y values that share that X value. That's the confidence interval. So based on a sample of male weights, let's estimate the weight of an individual male in the population, the mean weight of all males in the population. For these, we don't need regression, right? Here in our sample, we have mean of 170.8, standard deviation of 33.1. The distribution is close to normal. So what interval should contain the weight of an individual male? What we would expect for an individual male, that the mean would be about 170.8. Because the distribution is close to normal, we can use the 68, 95, 99.7 rule. So a 95% confidence interval would be 170.8 plus or minus 2 standard deviations, which would give us an interval of 104.6 to 237.0. For the mean weight of all males, if we have 162 in our sample with mean 170.8 and standard deviation 33.1, what interval would contain the mean weight of all males? Well, we need to know the sample size here. It's 162. So to compute that 95% confidence interval for the mean, we'll do 170.8 plus or minus 2 standard errors for sample means. So that would be 33.1 divided by the square root of the sample size, which gives us a confidence interval of 165.6 to 176.0. Notice that this is much, much, much narrower than the interval for an individual. That's because we're dividing by the square root of n, that's the sample size, and that was a pretty big sample here. Now let's look at an example that considers both height and weight. So we want to estimate the weight of an individual male that's 71 inches tall. Now, because these next 4 examples each involve a relationship between 2 quantitative variables, we'll need to use regression. So here again is a picture of our scatter plot and the least squares regression line. Now here is the regression line and the associated statistics. R is positive 0.45, so it's not a terribly strong relationship. But P is essentially 0, so the evidence for that relationship is very strong. The equation of our line is minus 188 plus 5.08x, and the typical residual size S is 29.6 pounds. So how much heavier is a sampled male for each additional inch in height? Well, remember that that's exactly how we interpret the slope. So for every additional inch, that's an increase in x of 1 unit. We would expect an increase because of the plus sign in the regression equation, an increase in the predicted y value of 5 units, so 5 pounds in this case. Y is S, that's the typical residual size, less than SY, the standard deviation of all of the y's. Well, in that case, remember that SY describes how all of the y values are spread, but S tells you how far a typical point is away from the regression line. Because we do have evidence of a linear relationship, and R is not 0, that means since R is positive, as we move from left to right as x increases, we expect the y's in general to increase. So the spread around the regression line will tend to be smaller than the overall spread in all of the y values. Finally, what interval should contain the weight of an individual 71-inch tall male? Well, notice that we've got 2 intervals in our output, a confidence interval and a prediction interval. The one we want is the prediction interval because we're looking at an individual. So looking at the same situation, how could we approximate that prediction interval by hand if we didn't have software to do it for us? Once we get that approximate interval, we'll check and see how close it comes to the actual interval given by the software. So how do we compute it? Well, first, to get any sort of confidence interval or prediction interval, and here we're looking at a prediction interval, we need to start by figuring out the center of the interval. That's the part that comes before the plus or minus. To find that here, we will plug 71 in for x into our regression equation. That gives us a y hat value of 172.7. That's the number that'll go right in the middle. Now, to get the 2 endpoints of the interval, we'll add and subtract some number. The number that we'll add and subtract is a multiplier times the standard error. In this case, the standard error will be the typical residual size. For the 95% prediction interval, we'll use a multiplier of 2. So that gives us 172.7 plus or minus 2 times 29.6, which gives us the prediction interval 113.5 to 231.9. And sure enough, that's not too far off from the prediction interval that was given by the software. Now let's move on to estimating the mean weight of all 71-inch tall males. Notice the difference between this example and the previous example. In the previous example, we were looking at individuals, and in this example, we're switching over to means. So if I look at all of the 71-inch tall males in the population, and I took their average, what would we predict would be the weight? So we're looking at the same situation. Now, what interval would contain that mean weight? Well, when we're talking about the interval that contains the mean weight of all 71-inch tall males, we're talking about the confidence interval. Now, how would we approximate that confidence interval by hand, and does it come close? Well, there is the confidence interval that's given by the software. It's 168.2 to 177.47. To approximate it by hand, we first plug in 71 to get y hat, and just as before, it's 172.7. That'll be the center of our interval. Now, instead of adding and subtracting the typical residual size, we want to take into account the size of the sample. Since the sample size was 162, we will divide by the square root of 162 in that margin of error there. And that gets us a confidence interval of 168.0 to 177.4. And sure enough, that's pretty close. It's not exact because, again, the multiplier for the 95% confidence interval, just like for the 95% prediction interval, it's not exactly 2. It's a little bit different from that. It's more like 1.96 for the z distribution, which would be appropriate here because the sample size is so big. And like we said, that's very close to the actual confidence interval. So here, the green star, it might be a little bit hard to see, so let me make it a green circle right there. That's what we predict for the center of both the prediction interval and the confidence interval for weight, given that the height is 71 inches. Here's what the prediction interval looks like on the scatter plot, and you can see that sure enough it contains all the data. Remember, we expect it to contain about 95% of the data. The confidence interval for the mean is much, much narrower. You see it there in red. Again, that's where we think the average value of the weight for all members of the population with height 71 inches will be. Continuing with this example, here's the equation of our regression line. Remember, for a height of 71 inches, we saw that we would estimate the weight to be 172.7. That's what we get when we plug in 71 for x. Now the question we want to ask is, how much heavier will our estimate be if we look instead at someone with height 76 inches? Well, remember the slope was around 5. And every additional, the way we interpret that slope is that every additional inch in height will result in an additional 5 pounds in weight. So if we add 5 inches to height, that would result in 5 times 5, or 25 more pounds for 76-inch tall person in the population. So instead of the estimate that we had at 71 inches of 172.7 pounds, we'll add 25 to that and get around 198 pounds. So we've gone from estimating the weight of an individual male at 71 inches tall to estimating the weight of an individual male at 76 inches tall. We would expect that person to be about 25 pounds heavier than our 71-inch tall person. So using software, we can find a confidence interval and prediction interval for height 76 inches. There they are. Which one of those would we want to look at if we're trying to guess the weight of an individual male that's 76 inches tall? And let's take a look at how that compares to the corresponding interval for height 71. Well, remember, if we're looking at an individual male, we're looking at a prediction interval. So that's the one we want to look at. There's the prediction interval for the weight of an individual male that's 76 inches tall. Notice that the predicted weight is sure enough about 25 pounds heavier than the predicted weight for someone that was 71 inches tall. You should notice the difference here between the numbers in the boxes. And notice that the corresponding prediction intervals also change by about the same amount. Now, again, looking at these same intervals, the confidence interval and the prediction interval for a person with height 76 inches, how could we get that interval by hand? Is our by hand approximation close to the actual value that we expected? Well, as before, we will find y hat, and we'll find that by plugging in 76. That'll give us the center of our interval, 198.1. From there, we'll add and subtract two standard errors. That's the typical residual size. And we get 138.9 to 257.3. And sure enough, those are real close to the actual value given by the software. Now let's move from individuals to means. If I look at all the 76-inch tall males in the population, let's find some interval approximations or some interval guesses for the mean of all of those 76-inch tall. So again, with the same output from the computer, which of these intervals would we expect to contain the mean weight of all 76-inch tall males? If we wanted to approximate that interval by hand, how would we do it? And let's check and make sure that our approximation is a good one. So the interval which we would expect to contain the mean weight of all 76-inch males, well, that's the 95% confidence interval, 188.58 to 207.84. To compute it by hand, as before, we'll get the center by finding y hat that corresponds to x equals 76. Plug in 76. That gives us y hat as 198.1. Now, instead of adding and subtracting 2 times s, we'll make sure we divide by the square root of n. That's the square root of 162 in this case, which gives us an interval of 193.4 to 202.8. How'd we do here? This seems like it's a little bit off. Each of the numbers seems to be off by about 5 pounds. Why? Well, at 71, that's right near the center of our scatter plot. Prediction interval is tall, as we see here. The confidence interval is narrower, as we expected. If we move up to 76, though, now look at our new green star. If you're having trouble seeing it, it's right here. What do you notice out there? There's the prediction interval. There is the confidence interval. Why is it wider? Why is it so much wider? Well, the problem is near the center of the scatter plot, we have a whole lot more data. Out near the edges, that's at a height of 76, there's not as much data to go on. That means we're less confident about where the mean will be. The prediction interval is still about the same, but the confidence interval for the mean is going to have to go up a bit. So we might look for interval estimates for individual responses to a given x value. So I know what x is. I want an interval that will contain most of the corresponding y values. If n is large, we can go start at y hat. That's what we get when we plug in x into the regression equation, and go up and down by 2s, where s is the typical residual size. We might also be interested in what the mean will be in the population, or the subpopulation, that all share the same given x value. To get that confidence interval, not prediction interval, confidence interval, we will divide s by the square root of n in that computation. So it looks pretty much the same. The difference is dividing by the square root of n. Now remember that as we move away from the mean, these approximations are not as good. The farther away from the mean we are, the worse these approximations are, especially the one for the means. That's the confidence interval. So let's look again at our scatter plot. So here we see right in the middle, the line that's not dotted, right there, that's the regression line. Now the big dotted line, the wide dots, up high and down low, now highlighted in blue, that's what we get if we go up and down about 2 times s. So that's the prediction interval for individuals. And we notice that it looks pretty stable as we move across from left to right. It goes up with the same slope as the regression line. Now if we look at the dots that are closer together and smaller, this is the upper bound and lower bound for the confidence interval. That's for the mean. Now something I want you to notice about this is that as we move away from the mean, remember the mean is right in here and around my green circle, notice that the dotted lines start to move farther apart as we move away. That's because as we saw in the previous example, the margin of error in the confidence interval goes up as we move away from the mean. So let's wrap up this big, long example. We talked about how to get a confidence interval for the weight of an individual male. This is looking only at the y values, not the x values, so we're only looking at the weights. We can get a confidence interval for the weight of an individual male. So you want to think about that as that 95% confidence interval, as if I were to pick a random person in the population, there'd be about a 95% chance that that person's weight falls in this range, 104.6 to 237. We also know how to get a 95% confidence interval for the mean weight of all males. We talked about that when we first did confidence intervals for single quantitative variables. And notice that the confidence interval is much narrower for the mean. That's because we divide by the square root of the sample size. Now, when we include height in into the mix, we need regression, because now we're looking at a relationship between two quantitative variables. If we know the height, we can estimate the weight by using the regression equation and use that as the center for our confidence interval. And now, instead of the standard deviation of all the y's, we're going to look at the typical residual size, s. So here was our 95% prediction interval for the weight of an individual with height 71. Notice that that prediction interval for the individual is quite a lot narrower. That's because I have additional information. That's the height. We would expect to be more confident in our pick. We can get a confidence interval for the mean weight. It's 160, for, again, given that the height's 71, 168.2 to 177.5. And again, that's narrower than we saw before. That's because the height was given. We have extra information that increases our confidence. Similarly, if the height is 76, we get a slightly wider prediction interval because we're moving away from the mean. And we get a significantly wider confidence interval, at 76 because confidence intervals are more affected by that distance from the mean. Let's take a look at this graphically. Here at the top, we see the 95% prediction interval and confidence interval if we don't use regression at all. That is, we don't use any information about the height. So that is up here at the top. And the other two are the intervals that we get when we do use height information. The middle intervals are for 71 inches. The bottom one is for 76 inches. And here we see graphically what we talked about on the last slide. Confidence intervals, that's the one for the mean, they're always more narrow than prediction intervals. If we use height information, both the confidence interval and the prediction interval will get narrower. Also, if we use height information, the center of the intervals will change. As we move far away from the mean, the farther we are from the mean, the wider the prediction and confidence intervals are. The confidence interval in particular is affected by this change. So here's an application. A news report stated that Michael Jackson was a fairly healthy 50-year-old before he died of an overdose. His 136 pounds were in the acceptable range for a 5'9" man. Using the equation we've been working with for the relationship between height and weight, do you agree that 136 is acceptable? Well, 5 feet 9 inches is 69 inches, so we can plug that in for x and get a predicted y value of 162.52. That's certainly well above 136. But let's look at the prediction interval, which takes into account the error. If we add and subtract 2 times the typical residual size, we actually get a prediction interval of 103.32 to 221.72. 136 is well inside this interval. Now, keep in mind that weights are not going to be distributed normally. For any given height, weight tends to be distributed in a way that is skewed a bit to the right. Heavier people at a given height are more common than really, really skinny people. You can see that in the scatter plot. There aren't very many points with a big residual below the line, but there are plenty of points with big residuals above the line. Okay, so let's start by looking at these problems in Excel. So I've put my data here in my spreadsheet. If you want to pause the recording for a second, make sure you've got these typed in correctly, go ahead and do that. Now, before we go and do some hypothesis tests or anything like that, let's start by actually checking the scatter plot and seeing if we have a relationship that looks like it's linear. So I'm going to select all my data. I'm going to go to Insert up here at the top, and I'm going to choose a scatter plot. There it is. If there is a linear relationship, it doesn't look like it's terribly strong. I do see that the points do tend to go up as we move from left to right, so I think there might be a slight positive correlation. So let's take a look at the strength of that relationship by inserting our trend line. So I'm going to right-click on one of the points. And I'm going to go to add trend line. So there is our regression line. It's dotted there. I'm going to go and click on display equation on chart so that we can see the equation. There it is. And display r squared on the chart. So r squared is 0.2649. If r squared is 0.2649, whoops, I did that wrong. If r squared is 0.2649, then what's r? Well, r would be the square root of that. I know it's the positive square root because the slope is positive. If it had been a negative slope, we'd use the negative square root. But that gives us an r value of 0.514. So remember, our dividing line between a weak relationship and a strong relationship was about 0.7. So this is a fairly weak relationship. I notice also that the slope is pretty close to 0. And remember, a slope of 0 tells us there is no linear relationship. So if we're going to do a hypothesis test, that's our null hypothesis, that the population slope is actually 0, and that our sample just happened to have a slight positive relationship. So let's scooch this out of the way and actually do a hypothesis test. So to do this, let's go into our data tab, and we want data analysis. Scroll down and find the option called regression. There it is on mine. I'm going to click OK. And it's going to ask you for a few things. First, it's going to ask you for the Y range. So I've already put it in here, but let's go back and show you how to do it. Click and drag over all the Y values. I've included the label up here at the top. If you do that, you can or can't. It doesn't matter. Just remember which one you do because you have to tell it later on. And then the X's, we have our X's here. Here's the check mark for labels. I did include my labels, so I want to check that. If you did not have any labels, if you just put the numbers, make sure that labels is unchecked. I want a confidence interval for the slope, so here's the chance to put in a 95% confidence level. Make sure that's checked. And then output range, just pick a cell that's up here near the top somewhere. If you want to play around with some of these other options, you're welcome to. Just check those boxes and click OK. You can see what they do. But for now, we're not going to need them. But I'm going to click OK, and it's going to spit out a bunch of stuff here. So let me walk you through what we found. You don't need to worry about that multiple r, but you do see that r squared is the same as ours that we got before. You don't need to worry about the adjusted r squared, but the standard error here, that's important because that is our typical residual size. Remember, that's S. And then the number of points. There's an analysis of variance here. We don't need to worry about that. We're not going to use it at all. But down here at the bottom, that's where the good stuff is for us. So notice that we have rows labeled intercept and payroll. So remember, payroll, that was our X value. So we're about to talk about the coefficient. The coefficient for the X value is how we describe the slope. So right there, the coefficient for payroll, notice that is the slope of our regression line. You see it down here. The intercept, that's the y-intercept. The y-intercept is 64.773. We saw that before as well. Now in the next column, we have standard error. We're not going to use the standard error for the intercept. That doesn't matter for us. But the standard error for the payroll is important. That's sort of our give or take number on the slope. So now for the hypothesis test, our test is that there is no, the null hypothesis is there is no relationship. That is, the slope is 0. Testing against that null hypothesis, we get a t-value for the slope of 2.24 after it's standardized. And again, we're using the standard error to standardize. That results in a p-value of 0.04. So that does fall under our threshold of 0.05, so we would say this is statistically significant. It's not statistically significant by much, but it is significant. Another way to see that is to look at the confidence interval. These next two columns give the 95% confidence interval for the slope. The lower value is 0.0099. The upper value is 0.4299 when you round off. And notice that 0, that's the value under the null hypothesis, the slope is 0, falls just below this 95% confidence interval, just barely. Well, that matches up with what we just saw. The significance was borderline. It's there, but it's borderline. We see it again here in the confidence interval. I have no idea why these numbers get repeated here, but you can ignore the last two columns. All right, so now we have found that there is a relationship. We can now predict, as the next part of the example said, the value, the number of wins for a team with a payroll of $90 million. So if payroll is 90, then how many wins do we expect? Well, the number of wins we would expect is the intercept, that's the coefficient on the intercept down here, plus the slope, it's 0.2199, times the x value. So we would predict a number of wins of 84.56464. Looking back at our data set, the Giants had a payroll close to $90 million, and their wins were 75. That seems kind of low. And if you look over here around $90 million, I think that point right there is the one that corresponds to the Giants. Yep, sure enough. That's the 90.2, comma 75. You do see it's low. But if you look at this point, which is 92.107 and 100, that's the Cardinals. So their payroll was pretty close to $90 million, and their number of wins was 100. So that was quite a bit above what was predicted. So there is the predicted number of wins. So that's y hat right there. Now, let's do our prediction interval and our confidence interval. So prediction interval, confidence interval. Now for the prediction interval, we're going to start at the center, which is the predicted value. And we're going to subtract 2 times the standard error. To get the upper endpoint, we'll do the center plus 2 times the standard error. So there is our 95% prediction interval. And there again, you see the Cardinals just sort of sneaking in under there. I know that prediction is 90 and not 92. But that's right at the upper limit of what we would expect. Now the confidence interval for the mean is a little bit different. Instead of being, instead of just adding and subtracting 2 times that standard error, we're going to start at the center of the interval, that's the predicted value, minus 2 times the standard error divided by the square root of the size of the sample. And the size of the sample is here in the number of observations. And for the upper limit, we'll do the same thing except with a plus, equals the center plus 2 times the standard error divided by the square root of the sample size. So there you have it. Hypothesis test for regression. We found the equation of the regression line, the t-value for the slope, and the p-value for the slope. That's testing whether there is a linear relationship. We found a confidence interval for the slope. We found prediction interval and a confidence interval for a payroll of $90 million. So that's the number of wins that we would expect to see for an individual team, between 69 and 100 wins roughly, and a confidence interval for the mean number of wins for a team that spends $90 million. That's 80.6 to 88.4. Okay, so now let's do the same thing using our calculators. The first thing to do is to enter our x values and our y values into our L1 and L2. So I'm going to go to Stat and Edit. I've already punched those in, so you might want to go through and do the same. If you need to pause the video and go back to the previous slide that had the data on it, let's go ahead and do that. When you come back, if you want to check and make sure that you entered correctly, go to Stat and go over to Calculate Two Variable Statistics. And you should see the sum of the x's, that's the second line, is 1135.17. The sum of the y's, if you scroll down, should be 1286. Now, once you've done that, your calculator will compute the equation of the line and perform the hypothesis test that we want at the same time. So let's do that. I'm going to go back into Stat. I'm going to go over to Tests. And it's easier to go up from here. We're looking for the linear regression t-test. I'm going to choose linear regression t-test. It's going to ask where the x's are and the y's are, L1 and L2. If you've done it like me, the frequency should be 1. Now, the next is the alternate hypothesis. Generally, this is going to simply be is not equal to. Either there is a relationship between the two variables or there is not. If you want to do a one-tailed test, you can do that too, but we're going to do the two-tailed test here. Now, the next thing here is the regression equation. You don't have to put anything in here if you don't want to. However, if you put y1 here, and you can find y1 by going to variables, I'm going to do variables, y variables, function, y1. What that will do is it will, when it computes the regression equation, it will copy and paste it into y1 in your y equals menu here. That can be a useful thing. And I'm going to go to Calculate and hit Enter. So here's what we get. We get the form of the equation is y equals a plus bx. Here's our alternate hypothesis. Remember remember beta is the slope in the population, rho is the correlation coefficient in the population. I don't think we've seen that yet. Regardless, remember the alternate hypothesis can be framed in both ways, that the slope is 0 or not 0, and that r is not 0. But we get a t-value of 2.246, that's just what we saw with Excel, and a p-value of 0.041355, that's also exactly what we saw with Excel. So we would interpret it in exactly the same way. If you scroll down, you see A, that's the intercept, is 64.773, and B is 0.2199, that gives us the equation of the regression line. There's S, that's the typical residual size. That's a good thing for us to know for computing intervals here in a moment. And it also gives us R squared and R. So everything we want to know about this regression, this linear regression t-test gives it to us. So now if you click on y equals, you'll see that sure enough, this equation in all its extra decimal glory has been copied and pasted into y1. So if we want to graph this thing, we can. Yeah, why don't we go ahead and do that? So we've already got the data in L1 and L2. Let's pick an appropriate range. So let's go to Window. Our X's, that was the payroll. Looking at the data, the minimum payroll that I see was at 38, and the maximum was at 101. So let's go from a minimum of 30 to a maximum of, let's say, 110, and we'll count by tens. Now for the wins, those seem to range from, I see 67 maybe is the minimum, and 100 is the maximum. So let's do maybe 65 to 105. 65 to 105. Whoops. 65 to 105. I don't think counting by fives is a good idea. Let's count by tens. So now let's turn our stat plot on. So I'm going to do second, and you see stat plot up there above y equals. Plot 1 I'm going to turn on. So I hit enter while it's flashing on. That is a scatter plot. There's the scatter plot. X's are in L1, Y's are in L2, and I want the little boxes. So now we're ready to graph. There's the scatter plot. There's the line. Beautiful. Now, one of the things I asked you to do was to predict the number of wins for a team with a payroll of $90 million. So now that we've got the line plotted, we can actually do that by going to second calc. I want to calculate a value, and it asks for the X value. The X value I'm interested in is $90 million, so I'll put in 90 and hit enter. So there is our predicted value, 84.564, just what we saw before. So it might be worth writing that down, that 84.564, that is our Y value. Another thing that you might do, if you don't want to have to enter this Y value in over and over, 84.565 when we round up to 3 decimal places. 84.565, so 80, whoops. I'm going to exit out of this. 84.564, I think is what we said. I want to store that. You see your store button here on the left. I want to store that in, let's choose alpha. Let's put that in Y. That'll be easy to remember. So now whenever I push the Y button, it's going to return that 84.564. Great. So there's our predicted Y value. Now to back up a little bit, I asked for a confidence interval for the slope. We can compute that as well. Let's go to stat. Let's go to tests. And if you go all the way down to the very, very bottom, next to last one, linear regression T interval. That interval is the 95 or whatever confidence interval you want for the slope. Let's hit enter. X's are in L1, Y's are in L2. Confidence level is 95%, 0.95. Again, if you want to paste the regression equation in, it's going to compute it again here. Y1, that's fine. And let's go to calculate. And here again, we see the same interval we got with Excel. 0 is just outside the lower end of that interval, like we expected to see. But there is our 95% confidence interval for the slope. Notice we also get B, that's the slope, and A, that's the intercept, and S, that's the typical residual size. So if those are the things you need, you can also get them from T interval. And if you scroll down, you also get R squared and R. So for our team with a $90 million payroll, let's get a prediction interval for the number of wins. So remember, to get that prediction interval for the number of wins, we take our center, which remember we stored in our Y register, so Y, and now we're going to do plus or minus. So let's start with the minus. It's 2 times the standard error. Remember, that was the typical residual size, right? So you can either just type it in, it happens to be right there, or once you compute this regression, it stores that in little s. We don't have a little s on our keyboard, but if you go under variables and go down to statistics, go over to equation. Nope, not equation. Test. It's in here somewhere. There it is. S. That would be the lower value of our 95% confidence interval. I'm sorry, 95% prediction interval. And now to get the upper endpoint, I want to do y plus 2 times s. But rather than type it all in again like a sucker, I'm going to use the entry function right above my enter key. That'll copy and paste the last thing. I'm going to just go back over to that minus, change it to a plus, hit enter, and there's our upper endpoint. Now, to get a confidence interval for the mean, remember that's the same formula except we divide s by the square root of the sample size. So once again, I'm going to use entry. I'm going to do it twice to go back to the second previous entry. And I'm just going to type on the end divided by the square root of 16 was our sample size. And enter. So there's the lower endpoint for our confidence interval for the mean. I'll do entry, and I'll go and change that minus to a plus. And there's our upper endpoint. So there's your confidence interval for the mean. For your extra credit questions, you'll need this set of data. I took this from our student survey data. It's a small subset of the data looking at math SAT and verbal SAT. We want to see if there's a relationship between the two. So take a moment, pause the video, and punch these numbers into either Excel or your calculator, depending on which one you want to use. Now, here are the questions. Here's a quick list of guidelines for performing inference with regression. Remember that the relationship between the two variables must be linear. It can't be curved. If it's curved, then while we can do all these computations, we definitely should not. The observations need to be independent and our sample needs to be random. Otherwise, our methods may not work. The sample size has to be large enough to offset non-normality. Typically, that means we need at least 30 points in our data set. In order to make sure that we get independence, remember that our population needs to be at least 10 times the size of the sample. The spread around the regression line needs to be more or less constant. We didn't see that so much in the previous example with heights and weights because the weights tended to be right skewed. We must remember also that outliers and influential observations might impact our results. So it's important to keep an eye out for those. Finally, we need to make sure we address confounding variables if it's an observational study. So to wrap up, we talked about regression for samples versus populations. Usually we know sample and we're trying to guess at population. We talked about how to use the slope and intercept and sample size in the sample, so the slope and intercept in the sample, how that affected our guesses about the population. We talked about hypothesis testing. Remember, the null hypothesis for regression is that there is no linear relationship between the two variables. In other words, the slope of the regression line is 0, or the correlation coefficient R is 0. You can state it in any of those ways. Remember that this is a test about the slope. Remember, the null hypothesis is the slope is 0. The alternate is that the slope is not 0. We talked about how sample slopes are distributed and how we can use that distribution once we standardize to find our p-values. We talked about how to use the output of regression inference. So the strength of the relationship given by R, and the strength of the evidence, which is given by P. That's the p-value in the hypothesis test. We computed a confidence interval for the slope. Then we turn to our intervals, the prediction interval and the confidence interval for y values given an x value. We talked about what they look like if you don't use the x value, and then how it changes if you do use the x value. We also talked about how x values near the mean or far away from the mean affected the sizes of the intervals. And we talked about how to approximate those intervals by hand. We saw that the confidence intervals were always more narrow than the prediction intervals. And we went through a set of guidelines for using inference in regression.